All right, so let's give this a shot. But before we even talk about the pseudocode, remember, I don't know if you watched the early videos in this section, but I talked about a priority queue and how that plays a role in the algorithm. Here's where it comes in. When we talk about picking the smallest value here, like if we go back, I don't know, like here, where we had to pick the next smallest value. So we visited A, C, and B. We need to look at the rest and figure out where we go next. Well, we had 4 for D, 7 for E, and 6 for F, so we chose D. That's 4. This is very easy to do with 3 nodes, but if we have a million that we're keeping track of, finding the next smallest one to visit can take a lot of time if we're doing it naively. So I'm going to do 2 implementations. Here's the first version. So I hit next through all my slides. Here's our simple priority queue. And we're going to start here so that we don't get too distracted. But this is going to give us the next node to visit. And all that it does, it's just an array. And every time you add something to it, you give it a priority. And then we sort based off of that priority, which is what happens here. So every time we insert, we resort. And then we remove from the array. So I've copied it over here just so you can see it. And if we do something like, I don't know, var queue equals new priority queue, like this, and then I do queue.push. When I push, or actually it's called enqueue. When we enqueue something, let's say just the node A, or let's not do A, let's say B, which has a distance, I'm just gonna say of 3. I don't think that's accurate. That's the priority that we add in. And now we'll also enqueue C, which has a distance of 5. Let's do D, which has a distance of 2. And then also, I don't know, Q, which has a distance of 20. Now, if we look at Q.values, you'll see that it's sorted now based off of that priority. So every time we insert something, it resorts. So if I insert something again, that's really small, like in Q, let's say P has a distance of 1.5, that's going to jump to the very beginning if we look at values again. Right? So every time we dequeue, these are the 2 methods we'll be using. Sort is used internally, enqueue and dequeue. When I do a dequeue, it's going to give me whatever has the lowest priority. We want the smallest item. So what we'll do in our pseudocode is just push in these values, like going back here. Let's suppose, ignore the fact that we visited all of these. Let's say all of these were in the queue. When we dequeue, we want whatever has the smallest distance from A. That's what we're prioritizing. So the priority queue is going to help us. And this is not the best implementation. It's simple. But remember back in the binary heap section, if you watch that, there's a better way, a faster implementation for a priority queue using a heap. This right here, because we're sorting every single time, it's O of n log n, which is not ideal, but it's simple, so we're going with this, and then we'll update our code to use the binary heap in a bit. Okay, so one more time, every time I dequeue, it gives me whatever the current smallest priority is, but if I insert something else, and I dequeue again, if that's smallest, I should get that next. So we'll take advantage of this in our code. Okay, so that's the naive basic priority queue. The goal is just to always get the smallest value out first, no matter what else is in there, just give us the smallest thing first.